Okay, hi everyone. So our next topic is X NOR gate. Okay, so X NOR means XR gate followed by XR gate followed by NOT gate. Okay. Otherwise, XR plus NOT gate, which is equals to X NOR gate. Okay, so we have alternate names. First one is odd number of ones detector or even number of ones detector, and the second one is equivalence gate. Equivalence gate, and third one coincidence logic circuit. Coincidence logic circuit, this is very important. Okay, coincidence logic circuit, otherwise coincidence gate. Okay, and the next one is logic symbol. So this is so additionally we need to add one bubble here. Okay, same as XR gate only, but we need to add one bubble in front of that particular logic gate. Okay, and these are the input variables, and here the output y equals to a x NOR b. Okay, otherwise you can write like this. Okay, a x NOR b. So x NOR symbol is what? Dot encircled. Okay, so this dot encircled can be used for X NOR notation. Okay, otherwise you can treat like this also, y equals to a XR b complement, like this also, no problem. Why? Because so this XR gate followed by NOT logic, right? This is XR gate a b. So here our logic y equals to what? A XR b. Okay, now which is followed by NOT gate, so that we will get a XR b whole bar, right? So this we can able to write like a X NOR b. Okay, this is your complete X NOR logic. Okay, now we can move for truth table. Second one, truth table. Okay, first input columns, after that output column y equals to a x NOR b. Okay, and here we have 0 0 condition, 0 1 condition, 1 0 condition, 1 1 condition. Okay, these are the four possibilities. Okay, now so here you can observe one thing. So a XR b equals to what? A b bar plus a bar b. Now a x NOR b equals to a XR b whole bar, right? A XR b whole bar is nothing but a b bar plus a bar b whole bar. By using complementary theorem, we can write like this: a b bar whole bar into a bar b whole bar. Okay, so జస్ట్ ఇక్కడ నేను కాంప్లిమెంటరీ థియరాన్ని అప్లై చేస్తున్నాను. ఓకే, ఈ ఎంటైర్ సమ్ కి ఇక్కడ కాంప్లిమెంట్ తీసేసుకుంటున్నాను. అప్పుడు ఏమవుతుంది, ఈ సమ్ వచ్చేసి ప్రోడక్ట్ అయిపోతుంది. ఓకే, కాంప్లిమెంట్స్ వచ్చేసి డిస్ట్రిబ్యూట్ అయిపోతుంది, రైట్? సో దట్ మీన్స్ ఏ బి బార్ హోల్ బార్ ఇంటూ ఏ బార్ బి హోల్ బార్. ఇప్పుడు మళ్ళీ ఇండివిజువల్ గా కూడా మీరు అప్లై చేయండి. ఇక్కడ ఏ బి బార్ అనేది ప్రోడక్ట్, రైట్? ఏ అండ్ బి బార్ వచ్చేసి ప్రోడక్ట్ లో ఉన్నాయి. ఓకే, ఈ ప్రోడక్ట్ కి మనకి హోల్ బార్ తీసేసుకున్నారు. ఇప్పుడు కాంప్లిమెంటరీ థియరం దీనికి అప్లై చేస్తే ఏమవుతుంది, సో ప్రోడక్ట్ కాస్త సమ్ అవుతుంది, రైట్? సో ఏ బార్ ప్లస్ బి బార్ హోల్ బార్. ఓకే, అండ్ ఇన్ ద సేమ్ వే అండ్ దిస్ వన్ ఏ బార్ హోల్ బార్ ప్లస్ బి. ఓకే, సో నౌ ఏ బార్ బి బార్ హోల్ బార్ అంటే ఆబ్వియస్ గా మనకి ఏమవుతుంది, బి వచ్చేస్తుంది. ఏ బార్ హోల్ బార్ అంటే 2 టైమ్ కాంప్లిమెంట్ చేస్తే సేమ్ థింగ్ ఎగ్జిస్ట్ అవుతుంది, రైట్? సో ఏ ప్లస్ బి వస్తుంది. ఓకే, సారీ, wait a minute, sorry, this one is b bar, right? So now here we are getting b bar. So this is your a x nar b logic, right? But this is in product of sum case, right? So these are the two sum terms which are multiplied, right? So that this is a product of sum. Okay, now for same thing we need to calculate sum of product equation, right? So first you can take this a x nar b in product of sum, that is a bar plus b into a plus b bar. So now you can simplify this entire equation. Then what you will get, a bar into a, right, plus a bar into b bar. Now b into a plus b into b bar. But according to AND operation theorem, a bar into a is nothing but what, 0, and b into b bar is nothing but what, 0. Then what you will get, a b, this is a b term, plus this one is a bar b bar term. So a bar, so b bar. Okay, this is your a x nar b sum of product nature. Okay, this is in sum of product nature. Okay, so in the previous XOR case, what you will get, so XOR gate, if you observe, so a XOR b is nothing but what, a b bar plus a bar b. This is for sum of a product. When comes to product of sum, so you will get a plus b into a bar plus b bar. This is for product of sum. When comes to X naught, a x nar b equals to a b plus a bar b bar, that is sum of product. And when comes to product of sum, a bar plus b into a plus b bar, right? So that is the difference. Okay, don't confuse with these equations. Okay, కొంతమంది ఏం చేస్తారు అంటే XR అనగానే AB ప్లస్ A బార్ B బార్ అలా బ్లైండ్గా గుర్తుపెట్టేసుకుంటారు. ఓకే, సో అక్కడ మిస్టేక్ అయితే చేయకండి. ఓకే, XR మీన్స్ A B బార్ ప్లస్ A బార్ B. XNAR is nothing but AB plus A bar B bar. Okay, so that is the difference. Okay, that means each product term having either complementary or uncomplementary variables. ఇక్కడ మీరు అబ్జర్వ్ చేస్తే ఫస్ట్ ప్రోడక్ట్ టర్మ్ రెండు కూడా అన్కాంప్లిమెంటరీ వేరియబుల్స్ ఉన్నాయి XNAR లో, అండ్ సెకండ్ ప్రోడక్ట్ టర్మ్ తీసేసుకుంటే రెండు కూడా కాంప్లిమెంటరీ వేరియబుల్స్ మాత్రమే ఎగ్జిస్ట్ అయ్యాయి. బట్ వేరస్ ఇన్ XR కేస్ one is complementary variable, another is uncomplementary variable. Okay, each product term will consist one complementary and one uncomplementary variable in XR operation. Okay, so but here completely different, either complementary or uncomplementary. Okay, and when it comes to product of sum term, so here both the sum that means each sum term will consist either complementary and uncomplementary. But whereas in X NOR case, each sum term will consist one complementary variable and another one is uncomplementary variable. Right? If you observe this particular term, A bar is complementary and B is nothing but uncomplementary variable. Okay, so that is the difference. Now you can apply this possible combination to this particular expression. So here expression is what? A B plus A bar B bar. Okay, this is our X NOR logic expression. So if you apply this 0 0 here, so A is equal to 0 and B is equal to 0 plus A bar B bar. So complement of 0 0, that means 1 1. So what you will get? 0 plus 1. So the final answer is 1. Alright, this is 1. In the same way you can solve remaining combinations also. You will get 0 0 1 here. For example, if you take this 1 1 condition, so this is 1 and this is 1. So complement of 1 means 0, complement of 1 means 0. So you will get 1 plus 0, so that you will get 1. Right. So once if you observe a previous gate, that means XOR gate. So for XOR gate we have a condition, right? So what is that condition? When both the inputs are same, output will become 0, right? When both the inputs are not equals, then the output will become 1. This is XOR logic operation, right? So but complement of XOR means, so this condition completely inverted, right? That means when both the inputs are same, A equals 0, B equals 0 and A equals 1, B equals 1. When both the inputs are same, the output will become 1. In the previous case, 0. That 0 is inverted in X NOR operation, so that we will get logic 1 here, right? So from these two conditions, we can able to write. So when both the inputs are same, when both the inputs are same, the output will become logic 1. Okay, if you observe these two conditions, then if both the inputs are not same, otherwise not equal, then the output will become logic 0. Okay, this is A equals to B case, right? And this one is A not equals to B case. So finally what we can conclude? If A equals to B, then Y equals to 1. If A not equals to B, then Y equals to 0. So this is for X NOR logic. Okay, so this is about X NOR operation. So this is your switching circuit diagram. A B bar switches and A bar B switches. If you compare with this logic expression, AB, so this is one product term and A bar B bar is one product term. AB product means already I told you. So product indicates a series connection. Okay, product indicates series connection and sum indicates a parallel connection. Okay, so here AB is the product term. So this is A switch and this one is a B switch. So these two are in series connection. If you ignore this A bar and B bar switches, then this AB forms a series connection, right? In the same way, if you ignore A and B switches, then this A bar B bar will form a series connection. Okay, and these two series connection switches are in parallel. Okay, how? So for example, if you look like, so this is your series connection. Okay, and this is your series connection of A B bar switches, and these two are connected with this common point here. So like this, okay, this is common point and this is common point, and this is connected to bulb and this is connected to source. Okay, so now if you observe, just you can twist the this particular circuit, then you will get like this. Okay, you will get like this, right? Okay, so that means what, these two are in parallel, right? So this AB plus A bar B bar series switches are in parallel, right? So just you can compare with our truth table, like, so A B and A X NOR B, so 0 0 0 1 1 0 1 1. So here the outputs are 1 0 0 1. So now you can compare with this particular table, so whether it satisfies or not. Just you can do that analysis. Okay, this is about switching circuit diagram of X NOR gate. Okay, now properties of X NOR gate. Properties of X NOR. Okay, so the first property here is A X NOR A, and the second property here is A X NOR 0, and third property here is A X NOR 1, and the fourth property here is A X NOR A bar. Okay, so you can solve these expressions. So here already you know about so y equals to A XOR B, that equals to AB plus A bar B bar. So this is your expression, right? Okay, this is your expression. So already we have a condition for this X NOR logic. If both the inputs are same, the output will become logic 1. If both the inputs are not equals, then output will become 0. If you observe the first condition, both the inputs are same, so output should be 1. Okay, here observe these fourth expression, both the inputs are different. First one is A and second one is A bar. That means both inputs are differ, so that the output will become 0. Okay, otherwise you can verify by substituting this expression also, you can verify, no problem. For example, if you take y equals to A is A only and B is equal to A bar here, okay, plus A bar is nothing but A bar only, and B bar is nothing but A bar whole bar, then you will get A only. Okay, this A into A bar equals 0 and A bar into A equals to 0, so ultimately y equals to 0. Right, in the case of this second expression, A XOR 0. Now first here the first variable is A and the second variable is 0. Okay, now you can substitute in this particular expression. So AB plus A bar B bar. So here A equals to A and B equals to 0 and A bar equals to A bar, right? Because A equals to A bar means A bar only. So B equals to 0, B bar means 1. Okay, so and this will become 0, A into 0. Something you can multiply with 0 means you will get 0 only, and A bar into 1 means you will get A bar. So A X NOR 0 equals to what? A bar. So this is A bar. Okay, in the same way you can perform A X NOR 1. In that case what happened? A into 1 plus A bar into 0, then this will become 0, so you will get A. So you can substitute A here. So these are the properties of X NOR logic, otherwise X NOR gate. And the one more important property, that is the fifth one. So here I am taking A X NOR up to n times. So which is equals to when n equals to even, and the second condition is when n equals to odd, then what is the expression value? So if n equals to even, already I told you in the previous example, so A X NOR A equals to what? 1, right? So now here For example, I will take n equals to 4. Here I am taking n equals to 4. In that case, what happened? A X NOR A and A X NOR A and A X NOR A. So these are the 4 E's, okay, which are in X NOR mode, right? So now, if you perform these two and if you perform these two, so A X NOR A is nothing but 1 X NOR, okay, and this one will become 1, right? So now both the inputs are same. When both the inputs are same in X NOR gate, y equals to what? 1. Here also input 1 and input 1. So obviously the outcome you will get 1 only, right? The output equals to what? Okay, the output will become 1. So when n equals to odd, in that case you can take 3, right? N equals to 3, in that case A X NOR A X NOR A. So if you perform for these two variables, so you will get 1 X NOR A. Already we have a equation. So 1 X NOR A is nothing but what? A, right? So what you will get finally? A only. So when n equals to odd number, then the outcome equals to A, right? So this is your fifth property, and some more properties also there. So those are here I am indicating. Note, here we have certain properties. A bar XOR B, and next A XOR B bar, okay, and next A bar X NOR B and A X NOR B bar, okay. So for these, so the outputs are A X NOR B, okay. Here A XOR B bar equals to A X NOR B, okay, and A bar X NOR B equals to A XOR B, okay. In the same case, here also A XOR B. So these are otherwise you can verify, okay. Just you can take one input is A bar, another one is B. Now you can substitute in your XOR operation, XOR expression, then you will get A XOR B, okay. So you can verify if you have any doubt, okay. So these are the 4 another properties, okay. And next, okay. So this is a GATE 2000 problem, and same question repeated in IES 2008. So for the logic circuit shown in figure, the required input conditions are A, B, C to make the output X equals to 1, okay. సో ఎక్స్ అనేది 1 మెయింటైన్ చేయడానికి కావాల్సిన ఇన్పుట్స్ ఏంటి అని చెప్పేసి క్వశ్చన్ అడుగుతున్నాం, ఓకే. ఎక్స్ అనేది మనకి ఇక్కడ 1 రావాలి అని అంటే, సో వాట్ ఆర్ ద కాంబినేషన్ ఆఫ్ ఇన్పుట్స్ ఆర్ పాసిబుల్ అని చెప్పేసి క్వశ్చన్ అనేది అడుగుతున్నాడు. ఇక్కడ మనకి ఇన్పుట్ కాంబినేషన్స్ అనేది ప్రొవైడ్ చేశారు, ఓకే. సో ఫస్ట్ ఎక్స్ అనేది 1 కావాలి, సో మనం ఇక్కడ ఇండికేట్ చేద్దాం, ఓకే. జస్ట్ యూ కెన్ ఇండికేట్ ఎక్స్ ఈక్వల్స్ టు 1, ఓకే. సో AND గేట్ అవుట్పుట్ 1 కావాలి అని అంటే కండిషన్ ఏంటి మనకి? సో AB అండ్ AB, right? So this is AND gate output, right? So 0 0 0 1 1 0 1 1, okay. So any one of the input is 0, the output will become 0, okay, for AND logic. If both the inputs are high, then only output will become high. But here we have 3 inputs, right? So we have 3 inputs for this AND gate, okay. So even 3 inputs also, okay, here the output will become A into B into C. If any one of the input is 0 out of A, B, C, if any one of the input is 0, obviously this product will become what? 0, okay. When this product will become high, all the inputs are high, then only this product will become high, right? That means what? So if x equals to 1, that is possible only when all the inputs of this particular AND gate is high, then only this x equals to 1 is possible, right? That means you can indicate here 1, 1, 1, right? If all the inputs are 1, then only the AND gate output will become high, okay? So that you can indicate 1, 1 here. So from this circuit, so here 1 means this will indicate here. So that means what? C equals to 1. So one thing is over. Just you can verify the options. So this is A and this is B and this one is C. So here C equals 1, but all the options C are common element, right? That means C equals 1, 1, 1. So you cannot eliminate the options, okay? Now you can move for second variable, that is B. So here we have 1, that means this X NOR gate output is 1, okay? X NOR gate output is 1, that means what? When X NOR gate output will become 1. So already we have a statement, right? That means if both the inputs are same, the output will become 1. If both the inputs are not equals, the output will become 0. This is for X NOR condition, right? This is for X NOR condition. Okay, so here we have one input is 1 for this X NOR gate, okay? So here the output also 1. So what is the second input here? So this one is this output X NOR gate output 1, that is possible only when both the inputs are same. Here we have 1. So here also we can expect 1. Then only we will get 1 here. Otherwise we won't get 1 here, right? So if both the inputs are 1, otherwise zeros. If both the inputs are zeros or if both the inputs are 1, then only output will become high. But already we have 1 here. So to satisfy this output high, so we need to take 1 here, right? So this 1 is connected to B terminal. That means B equals what? 1. Then B equals to 1. Now this is XOR gate, okay? XOR gate output is what? 1 here. So this one is connected to this gate. So that means what? XOR gate output is 1 here. So when we will get XOR gate equals to 1, when both the inputs are same, output will become 0, and when both the inputs are not equal, then output will become 1. This is for XOR, okay? This is for XOR logic. Already here we have 1 B input, okay? So here the output equals 1. To satisfy this output 1, so we need to take A value is different from B. That means B is equal 1 means here A equals to 0. Then only this output is possible. Otherwise this output is not possible, okay? So here we can take 0. So 0 and 1. So both the inputs are different, then the output logic equals to 1. Now from these inputs, A is equal to 0, B is equal to 1, C is equal to 1. So you can check. So 0, 1, 1. So D option is correct, okay? This is about X NOR operation. Here the next important note here is AND or XOR logics are follows associative law. That means associative law is applicable here. Associative law is applicable for these 3 gates, right? And when it comes to NAND, NOR and X NOR, these all are inverted operations, right? All are inverted operations for these logic gates, right? So these inverted operations are not follows the associative law. That means associative law is not applicable. Associative law is not valid for these 3 gates. Not valid for these NAND, NOR and X NOR gates. That means from these 2 points we can conclude that, for example, if we are taking A XOR B XOR C equals to A XOR B XOR C. So this is, that means this follows associative law. Why? Because here we are using XOR operation. We are using XOR operation, but XOR operation follows associative law. so that this expression is possible. A XOR B XOR C equals to A XOR B XOR C. So this is valid, right? In case if you are taking XNOR operation, A XNOR B XNOR C equals to A XNOR B XNOR C. So this is not possible. Why? Because here we are taking XNOR operation. For this XNOR operation, for this XNOR gate, associative law is not applicable, so that these two expressions are not equal. So here associative law is not valid, otherwise not applicable, so that this is not equal, right? Okay, so these are the two important points. So from this we can solve one problem, then you will get clarity about this particular associative law, right? So first, so if you observe this problem, so A XOR B equals to C, A XOR C equals to B, B XOR C equals to E, then A XOR B XOR C equals to what? So this is the question. First you observe the given one is XOR operation, right? So that means the given entire problem which involves in XOR operation mode only, right? XOR operation. Okay, XOR operation means associative law is applicable. Associative law is valid for this particular XOR operation, right? So if you observe this, A XOR B XOR C equals to what? But already we have A XOR B equals to C. Directly you can substitute here C, right? Now what you will get? C XOR C. So if both the inputs are same, output will become 0. So then A XOR B XOR C equals to what? 0. Okay, so that is the answer. So now when it comes to second problem, the given one is XNOR operation. Okay, the given one is XNOR operation. So that means what? Associative law is not applicable. Associative law is not applicable. Okay, that means you don't do the like this. Okay, that means if you add, if you take this XOR operation and add to this particular element, right, that is not applicable here. Okay, so that means most of the students will do same manner, like above manner, right? So మీరు ఇక్కడ ఏం చేస్తారు, A XNOR B ఉంది, దాని వాల్యూ C ఉంది ఇక్కడ. సో ఈ వాల్యూని డైరెక్ట్ ఇక్కడ సబ్స్టిట్యూట్ చేస్తారు. A XNOR B C. So C XNOR C means both the inputs are same, so that output will become. So this is completely wrong. Okay, సో అసోసియేటివ్ లా అనేది XNORకి అప్లికేబుల్ అవ్వదు కాబట్టి ఇండివిజువల్గా మీరు ఇట్లా వాల్యూ అనేది సబ్స్టిట్యూట్ చేయడానికి పాసిబుల్ అవ్వదు. యూ కెన్ పర్ఫార్మ్ ఎట్ ఏ టైమ్ దీస్ త్రీ వేరియబుల్స్. At a time you can perform XNOR operation among these three variables. Okay, then only we will get the outcome. Don't do like this. So A XNOR B, just you can substitute here. చాలా మంది అలా చేయడానికి పాసిబిలిటీ ఉంది. సో దానికంటే ముందు మీరు గుర్తుంచుకోవాల్సిన థింగ్ ఏంటంటే ఇక్కడ అసోసియేటివ్ లా అనేది అప్లికేబుల్ కాదు కాబట్టి ఇలా మనం టూ వేరియబుల్స్ XNOR ఆపరేషన్ వాల్యూని ఇక్కడ సబ్స్టిట్యూట్ చేయడానికి కుదరదు. ఓకే, సో సింపుల్గా చెప్పాలంటే ఇక్కడ XNOR ఆపరేషన్కి అసోసియేటివ్ లా అనేది అప్లికేబుల్ కాదు కాబట్టి ఈ వాల్యూని మనం ఇక్కడ క్యాలిక్యులేట్ చేయడానికి పాసిబిలిటీ లేదు. ఓకే, సో దట్ యూ హ్యావ్ టు రిమెంబర్. Okay, this is about associative law, so which is applicable for AND gate, OR gate and XOR gate, and which is not applicable for NAND, NOR and XNOR logics, right? So and okay, next realization of NAND and NOR gates. Okay, required NOR gates. Okay, so first one is NOT gate. Already I told you NAND and NOR gates are universal gates. With the help of these gates we can able to construct any digital circuit. So digital circuit will depends on basic gates and extra gates and universal gates. If you take any digital circuit, that will depends on logic gates only. Okay, with the help of logic gates only we can able to construct the digital circuit. So these are logic gates we can able to construct with the NAND and NOR, these two logics only. Okay, with the help of these two logics we can able to construct these all gates. So that's why we can able to construct any digital circuit with the help of NAND or NOR logic, right? So first, how you implement this NOT gate with the help of NAND and with the help of NOR. So I will explain only NAND gates. So you can try for NOR gates. Okay. So that means how to implement NOT gate with NAND, that I will explain. Same thing you can try for NOR gate. That means how this NOT gate implemented with the help of this NOR, that you can try at your home, right? So now first, so how many number of NAND gates are required to implement this NOT gate? So we required only one. Okay, one NAND gate is enough to implement this particular NOT gate. Okay, so that is like this is our NAND gate, NAND gate. Okay, so here we have two inputs. Okay, NOT gate means which is perform inverted operation, right? So here I am taking A, right, and here I am providing input 1. Okay, now what you will get here, A into 1 whole bar, so that you will get A bar. Here I am providing variable A, so finally I will get A bar. That means inverted or not. So otherwise you can consider in this way also. So you can take one NAND gate here. So you can tie up these two inputs to one particular variable. That means here I am providing A, here also I am providing A input. Okay, so here I am taking inversion. That means A into A whole bar. So already you know A into A means what? According to AND operation theorem, you will get A only. So that here you will get A bar. That means if you take two same inputs to this particular NAND gate, you will get inverted variable here. That means you can tie these two, but because same, right? So that I tie up with these two inputs and I will provide A here, right? So what you will get? A bar, right? So this is the way you have to implement not operation. There is not logic with the help of NAND gate, right? And in the same way, AND gate, how to implement this AND logic with the NAND gates. How many number of gates, how many number of NAND gates are required to implement this particular AND logic? Okay, so we require two NAND gates, right? We require two NAND gates. So generally AND gate is nothing but a product. If you take A and B are two variables, so the outcome is what? AB, right? Already we know. So Y, that means A is one input and B is another input. So then what you will get? Y equals to A into B. This is for AND gate outcome, right? So same thing you can implement with the help of NAND logic. First I am taking one NAND gate here. Okay, so for this I am taking two inputs, that is A and B. So finally what you will get here? A into B whole bar. That means inverted product. Okay, now you have to convert that into AB, right? In that case what happened? Already here already done NOT gate. So here I am providing same input to this particular NAND gate. Finally what I get here? A bar, right? If I am providing A here, so I am getting A bar. So in the same way you can directly provide input to one particular NAND gate. That means same input AB bar to NAND gate. Then what you will get? This is AB bar and this is also AB bar. So finally what you will get? AB bar whole bar. Then what you will get? AB. Okay, so here you are providing AB. So here the final outcome is what? AB. AB is nothing but what? That is AND logic, right? So in order to implement this AND logic, how many number of NAND gates are using? Two number of NAND gates are used here, right? So this is about realization of AND with NAND logic, right? So next, OR logic. Here we required three NAND gates. Okay, so now first I will take one NAND gate here. So here I am providing input A, and here also I am taking one NAND gate. Here also I am providing one input B. So A is applied to this particular NAND gate, so that I am getting A bar here, and here I am getting B bar. Okay, now these two are connected to one more NAND gate, so that is A bar into B bar into whole bar. Then according to complementary theorem, you will get A plus B, right? That means A bar whole bar and B bar whole bar, then A plus B. So inputs are AB and output is A plus B. That means sum. So implemented or not? So in order to implement this OR gate, we require minimum 3 NAND gates are required, and fourth one is NAND gate. For this we don't require any NAND gates. Why? Because NAND only, right? So to implement this NAND logic, we require NOR gates, right? So here we have NOR logic. So this NOR logic also can able to implement with the NAND. So how many number of NAND gates are required to implement this NOR logic? So we require 4 NAND gates. So NAND means what? Already we know NAND logic is nothing but what? Inputs are A comma B. Okay, if you are providing NAND these inputs to the NAND gate, so we are getting, sorry, not NAND, NOR. Okay, okay, if you are providing AB to this particular NOR gate, so you will get A plus B whole bar. Already we know. So NOR gate is nothing but OR gate followed by NOT gate. OR gate outcome is what? A plus B. OR gate followed by NOT gate means A plus B whole bar. So this is our outcome of NOR gate. Same thing you can perform with the help of NAND gates. Okay, already here we done A plus B. Okay, here we are getting A plus B with the help of these 3 NAND gates. But we need A plus B whole bar. That means what? We need one more NOT gate is required. So in order to implement NOT gate, one NAND gate is required. So you can same configuration you can take here. For this you can add one NAND gate, so that is enough to get this A plus B whole bar, right? So here I am taking now. If you observe, this is A and this one is B. Here you are getting A bar, here you are getting B bar. Now these two are applied to this particular NAND gate, so that we are getting A bar into B bar into whole bar, and which is equals to A plus B. A plus B tied to this particular NAND gate, so that we will get A plus B whole bar, right? A plus B whole bar is nothing but what? NOR logic. So with the help of 4 NAND gates, we can able to implement a NOR logic, right? So and in the same way, if you consider XOR gate means what? The logic here is what? Y is equal to A B bar plus A bar B, that equals to A XOR B. So this can be implemented with the help of NAND gates. So for that we required 4 NAND gates, right? 4 NAND gates are required. So here space is not enough, so that I will move on to next page to implement this XOR logic with NAND gates. Okay, so now XOR logic with the help of NAND gates. Okay, so first you can take one NAND gate here. Okay, so for this we need to add 2 inputs, one is A, another one is B. So here we are getting AB whole bar, right? Now, so I am taking one NAND gate here. and here also I am taking one NAND gate. So, and this AB bar is connected to both the NAND gates. Okay, one input, right? And next input I will directly connect it to here. So this is A and this is B. That means okay. So this is A and this is AB bar, and this is B, and this is AB bar. Now these two are connected to one NAND gate. Okay. So now what you will get here, A into AB bar whole bar, and here B into AB bar whole bar. Now if you simplify this, you will get A bar plus AB bar whole bar. Now that equals to what? A bar plus AB, right? And here also same thing, B bar plus AB bar whole bar. Now you will get B bar plus AB. So here the input is what? B bar plus AB. Now these two are connected to this last NAND gate. Then you will get A bar plus AB into B bar plus AB whole bar. Okay. Now if you simplify based on complementary theorem, what you will get? So A bar plus AB whole bar plus B bar plus AB whole bar. Now you can simplify further. So A bar whole bar into AB bar plus B bar whole bar into AB bar. Now A bar whole bar means A, and this AB whole bar, otherwise A bar plus B bar plus B into A bar plus B bar. Now from these two expressions we can take common A bar plus B bar as a common factor. Then what you will get? A bar into B bar, then A plus B. So if you simplify these two, you will get uh, A B bar plus A bar B. So this equals what? A XOR B. So in order to implement this XOR logic, we require 1, 2, 3, 4. 4 NAND gates are required. 4 NAND gates are required. Okay. So this is the implementation part. Okay. With the help of 4 NAND gates, so we can able to implement this XOR logic. And next one is what? XNOR logic. So to implement this XNOR logic, we require total 5 NAND gates. That means so here already we get XOR B, right? So we required A XOR B whole bar. Okay, to invert this particular A XOR B, we required one more NAND gate here. That means you can tie up with one NAND gate here. Okay, you will get that means this is A XOR B is applied to this particular NAND gate. So two same inputs, so that the outcome will become invert of this particular input, so that you will get A XOR B whole bar, right? So that means the final outcome is like this. So just you can take So this is about X NOR logic. So in order to implement this X NOR logic, so we require 5 NAND gates. Okay, so this is 1, 2, 3, 4, 5. Total 5 NAND gates are required. So this is the implementation part. So in the same way you can try for with the help of this NOR realization. Okay, so these are very important for entrance point of view. So to implement this XOR logic, how many NAND gates are required? That means 4 NAND gates are required. To implement this XNOR logic, how many NAND gates are required? 5. To implement this AND logic, how many NAND gates are required? 2. In the same way, to implement this NOT logic, how many number of NOR gates are required? To implement AND logic, how many NOR gates are required? To implement OR logic, how many NOR gates are required? Like that, you can realize this basic and extra gates with the help of this NOR logic, right? So I will give, so నేను hints provide చేస్తాను. ఓకే, అంటే ఎన్ని గేట్స్ రిక్వైర్డ్ అవుతాయనేది నేను ఇక్కడ ప్రొవైడ్ చేస్తాను, మీరు రియలైజ్ చేయండి. ఆల్రెడీ ఇది 5th అసైన్మెంట్ కింద మీకు ఆల్రెడీ ప్రొవైడ్ చేశాను. ఓకే, డెడ్ లైన్ వచ్చేసి ఐ థింక్ 15th or 20th ఏమో పెట్టాను. ఓకే, 20th May. ఓకే, ఒకసారి వెరిఫై చేయండి. సో ఇక్కడ రిక్వైర్డ్ నెంబర్ ఆఫ్ గేట్స్ ఒకసారి మీరు అబ్జర్వ్. ఓకే, మనకి ఇక్కడ నాట్ గేట్ ఇంప్లిమెంట్ చేయడానికి 1 NOR gate is enough. But to implement AND gates we require 3 NOR gates. To implement OR logic we require 2 NOR gates, and to implement a NAND gates, NAND logic we required 4 NOR gates, and to implement XOR, so for NOR we don't require any realization, and for XOR logic we required 5 NOR gates. For XNOR logic we required 4 NOR gates. Okay, so this is homework for you. Okay, so this is about logic gates. Okay, so 3 basic gates and 2 universal gates and 2 extra gates, and some properties as well as some important notes and realization of this basic and extra and universal gates with the help of NAND and NOR realization. Okay, this is all about logic gates. Okay, so all the best for your exam. Thank you.